Hi everyone, my name is Minghong Zhang. I'm from Bedford Institute of Oceanography. My cooperators are Will Perry and Zhang. Today's topic is the impact of Arctic climate change on synoptic cyclones and Beaufort High. As we all know, the Arctic has experienced dramatic climate change over the last few decades. Arctic sea ice had rapidly declined. The CMIP model had projected ice-free summer by the middle of 21st century. Also, the variation of the predominant Arctic atmospheric circulation, Beaufort High, have significant impact on sea ice motion and ocean circulation. Understanding the future changes in Arctic cyclone and uncertainty are important. However, we have been recognized that the current Coarse climate model tends to underestimate the frequency and intensity of Arctic cyclones. So in our study, we conducted a dynamical regional downscaling simulation of Arctic climate using Polar WRF, drawn by HadGEM Center's Earth System Model, following IPCC-5 historic simulation and climate scenarios RCP 8.5, 4.5, and 2.6. Here we use Polar WRF3.6, spatial resolution is 25 km. The right plot shows photo domain. Polar WRF results provide significantly improved simulation of Arctic cyclones compared to the HadGEM Center's Earth System Model simulation over the historical period. Next, I'm going to show future changes in Arctic cyclones from the simulation of Polar WRF. This slide shows climatology mean of winter low pressure and surface wind from the realized data year interim, HadGEM Center Earth System Model, and Polar WRF over the historic period and the last 3 decades of 21st century in the RCP 2.6, 4.5, and 8.5. We can see by the end of the 21st century, the Beaufort High becomes weakening with the increasing of RCPs. The resulting southwest wind prevail in the central Arctic Ocean instead of the permanent westerly wind in the current climate. Such changes are due to increased cyclones of the western central Arctic. Then let's look at the changes in cyclone frequency between the historical and 3 RCPs from the result of the HadGEM Center Earth System Model and the Polar WRF. We can see there is a decrease in cyclones over the Atlantic Arctic and an increase over the West Central Arctic and 3 climate scenarios. In addition, such patterns show a loss westward displacement with the increasing of RCPs. As a result of the compensation, there is no significant changes in the total numbers of Arctic cyclones. How about the changes in intensity of Arctic winter cyclones? The left columns show the histograms of the minimum central pressure in Arctic cyclone tracks, and the right column shows the estimated probability distribution functions of the minimum central pressure. The histograms show the increasing occurrence of the intense cyclone in the 3 RCP scenarios compared with that from the current climate in both model simulation. However, the probability distribution functions of the minimum central pressure in Arctic cyclone tracks suggest that there's a significantly higher probability of the cyclone track occurrence with a moderate minimum central pressure among 975 to 995 millibar in the HadGEM Center's Earth System Model RCP 8.5 and Polar WRF RCP 8.5 result, compared with the result from the historical simulation. We also want to point out that Polar WRF shows much larger overall intensity and much more intense cyclones, compared with the result from HadGEM's model in all the simulation. We can take a look at the physical reasons for the changes in Arctic winter cyclones from the eddy growth rate at the middle and low troposphere. Here we show the difference of the eddy growth rate between the last 3 decades of 21st century and 3 RCP scenarios with the historical period. We can see the eddy growth rate at the middle level decrease in the Atlantic Arctic and increase in the central western Arctic. Both the change in wind chill and the static stability contribute to the changes in the eddy growth rate. And the eddy growth rate at the low troposphere has robustly increased in most of the Arctic basin, and the increasing has become more robust with the increase of RCPs. The large reductions in the static stability account for the robust increase in the eddy growth rate at 925 millibar. Next, I will talk about the changes in the summer circulation. This slide shows climatology mean of the summer sea level pressure and surface wind from the United data year interim, HadGEM's model and Polar WRF over the historical period and the last 3 decades of the 21st century in the RCP 8.6, RCP 4.5, and RCP 8.5. We can see by the end of the 21st century, the Beaufort High tends to eastward extend, and such changes become significant in the RCP 8.5. It would result in the northwest wind of the Central Arctic Ocean instead of the prevailing westerly wind in the current climate. However, the responses of summer cyclones are not very robust in both the frequency and intensity. This slide shows the changes in cyclone frequency between the historical and 3 RCPs from the result of the HadGEM model and Polar WRF. We can see there is an increase of cyclone frequency over the western Central Arctic and Greenland Sea, and a decrease of the Norwegian Sea and the Western Siberia continent, and 3 RCP scenarios. There is no significant changes in the intensity of summer cyclone in both model simulations. The upper plot shows geopotential high at 500 millibar in the historical period and the last 3 decades of the 21st century and the RCP scenarios. The bottom plot shows the difference of 500 geopotential high between 3 RCPs minus the historical simulation. We can see, under the warmer RCP scenarios, the whole Arctic troposphere becomes warmer and the polar vortex becomes weaker. The Eurotrough becomes shallower, which is with more cyclones from North Atlantic into Greenland Sea, and less cyclones to the Norwegian and Kara Seas. As a result, the nicest event tend to increase over the Greenland Sea and West Central Arctic, and decrease over the Norwegian and Kara Sea in both the HadGEM model simulation and Polar WRF. This plot is not shown here. This can account for part of the changes in summer cyclones. Such changes in the pathways of Arctic cyclone can be seen from the cluster analysis. The cyclone tracks that originate from Atlantic Arctic can be classified into 2 clusters. The cyclones in the cluster 1 typically follow straight tracks across the Iceland Sea and travel to the Greenland Sea or the Nordic Seas and die there, while the typical track in cluster 2 is stirred by the upper flow parallel to the coast across Eurasia, and some will die in the Central Arctic, as shown by the mean regression purple curve of the cluster 2. By the end of the 21st century and the warming RCP scenarios, the cyclone tracks in Cluster 1 is more deviated towards the frame strait in comparison with the historical climate. In Cluster 2, there are more tracks traveling westward into the Central Arctic. This also accounts for part of the increased summer cyclones over the Central West Arctic. Now we go to the summary. By the end of the 21st century, in winter, Beaufort High becomes weakening, which is due to the increased frequency and intensity of Arctic cyclone in the western Central Arctic. The change becomes more robust with RCPs. In summer, the Beaufort High tends to eastward extend, and such change becomes significant in the RCP 8.5. The change in summer sea level pressure is due to two reasons. One reason is the increased cyclone frequency over the western Central Arctic and the Greenland Sea, and the decrease of the Norwegian Sea and western Siberia. The maximum thermodynamic warming of the Arctic troposphere of the Eurasian Arctic also makes a contribution. Thank you.